Thank you for viewing this recorded Reliable Automatic Sprinkler Company webinar. Should you have any questions regarding this presentation, please feel free to contact Reliable Technical Services at 800-557-2726 or email us at techserve@reliablesprinkler.com. For upcoming webcasts and an archive of past webcasts, please visit reliablesprinkler.com/webcasts. Once again, thank you and enjoy the presentation.
Good morning, and thanks for everyone for joining us. We're excited to be here this morning from sunny Liberty, South Carolina. Wanted to introduce ourselves. I'm Phil Friday, Director of Engineering Applications and Innovation here at Reliable. And I'd like to introduce the other panelists and co-workers on this project, Ken and Matt. Ken and Matt, you want to introduce yourselves?
Sure. My name is Ken Quist. I'm a senior product development engineer here. And I kind of worked on this project from taking the concept that these two gentlemen approached us with and massaging it into a final commercial product for us to sell.
Hi, my name is Matt Rouleau. I'm a technical services manager here at Liberty Reliable Automatic Sprinkler. Basically provide customer support on our product line. My involvement in this project was the preliminary design work for the racking systems and to do some preliminary flow collections to get us rolling on this project.
Yep. So from my point of view, you're kind of the genesis of this project. Can you take us back to maybe how this got on your radar and what led us down the path to saying, hey, this is a need out there in the market that we need to address?
Yeah, thanks, Ken. I wouldn't say I was the genesis, but certainly got to be on the ground floor of this effort, and it really goes back for me many years as an engineering consultant, and really in our personal lives. Lithium batteries are really everywhere. You see them in laptops. If you're watching this webinar now, whether it's either via recording or you're watching it live, chances are you're doing that with a device that's powered by a lithium-ion battery. And so as a consultant years ago, our clients would start to approach us about challenges that they were starting to see in the lithium battery space or with lithium batteries. But one specific example, we had a client who was in the e-commerce space, and they wanted to start using robotic material handling systems, automatic storage and retrieval systems that have robots that were going to be powered by and are powered by lithium-ion batteries. And then we've had other clients who are in the data center space, and they had large data centers and wanted to start using lithium-ion batteries as part of their uninterrupted power supplies, energy storage backup. And the questions they had at the time were really surrounding both the regulatory requirements and what do we need to do, if anything, to address those problems or potential issues. And so there wasn't a lot of information out there at the time. There wasn't a lot of enforcement of requirements or clear requirements around what to do. And so at the time, we sort of adopted a philosophy that consisted of two things. And one was when a lithium-ion battery goes in a thermal runaway, which is something that can happen, that's not an event that can be stopped. And it's going to quickly spread to adjacent cells. And so because of that, we started to look at it as, okay, this is our new ignition source, right? We've had all kinds of ignition sources to deal with in fire protection in the past, but lithium-ion batteries became, and I think continue to be, the new ignition source that you have to consider. And so that was, that's going way back.
So maybe how far back was where you started to see that come up in the industry in general? When did you start feeding those questions?
I think it's almost 10 years ago, and that it really started to catch everyone's attention. And then so if we fast forward to our time here at Reliable and how we got started on this, well, one of the first things that that we did, or I got to do, is when I came here a couple of years ago, was we had several customers who were starting to work on lithium-ion battery manufacturing plants. And so we got the opportunity to go look at some of those facilities, and it was really eye-opening to see what was in those buildings. They're huge. They're very large manufacturing facilities. And looking in those buildings, we could see that there were certain areas where they had challenges with fire protection. And so some of those areas were what they call formation aging and testing. And these are rooms that have floor to ceiling racks that feel like the size of a football field, and they had ceiling and in rack sprinkler protection. But these aren't your typical racks that you would see. And so there were challenges with the installation. And so we gathered as much information as we could. And when we looked at it, we said, gosh, there's got to be a better way to do this. So that's when we brought the information back. And then Matt, tell me about what you did with that information.
Sure. I mean, at that point, I had the opportunity to go ahead and take the information provided from Phil and the team and create AutoCAD drawings that we could build from. It was the start of the mock-up procedure from a CAD drawing to get some feedback for our layout, make sure we had the appropriate compartment size, clearances. And we went ahead and moved forward and constructed a wood model of that and brought that out into the flow lab. And at that point, we got the opportunity to start flowing sprinklers that we currently have, just to see what the collections would be like in that space. And we really quite quickly found out that there was some serious challenges to only trying to provide perimeter fire protection into those storage spaces.
With standard sprinklers.
With standard sprinklers. Yeah, we tried uprights, pendants, 5.6, 8.0, all the way up through K25 sprinklers. And being outside of the rack or compartment, we noticed again right away that 50% of that water is being sprayed outside of the space we're trying to protect. So I think that's really part of the reason that drove us to look at a different method of trying to protect that. We know that in these battery compartments, the clearance is a huge issue. So deflector to the top of storage is really a challenge for us. And our normal sprinklers, standard sprinklers that we were testing with to begin with, spray pattern wouldn't open up quickly enough. Whereas thinking about a horizontal sidewall, that spray pattern puts water in the direction we want it, and it also is right from the deflector out, opens up very flat, very, very quick space. So we found good results with that. And I think at that point, we decided to turn the ball over to the product development team.
I think one of the things that's worth pointing out as well is the idea of a horizontal sidewall was really interesting. It was an exciting new thing that hadn't been done before. And when you ran collections with existing horizontal sidewalls, those weren't great either.
Which is what was being used at the time, right? For hodgepodge things.
Yeah, you would see all kinds of things, but so tell me about what you did with when we said, hey, look, we need a horizontal sidewall sprinkler that's actually designed for this particular hazard.
Yeah, so when I jumped in there, they kind of were zoning in on this concept that of a horizontal sidewall into an in-rack system. And thinking about a horizontal sidewall in general, you're kind of looking to throw that water out there at pretty good distances. And now we're talking about somewhat bringing that back into the near field And that was one of the major challenges that we had to address. But, from a design standpoint, there was a lot of things that went on with this project that that really contributed to the overall success. And part of that was the collaboration we had with this group here. They laid the groundwork for some good baseline testing, and we were able to build on that, take that concept and start kind of learning fast, right? We would come up with a prototype. We'd go out to a lab, we'd run it, we'd get back together, we'd talk about it, we'd make a decision, and we'd do that all over again. And we did that many, many times. Something that's really helped us in this project, which is something we use on all of our projects, but particularly in this one, was the ability to use some additive manufacturing processes, some 3D printing processes to help us speed up that design iteration cycle. So we would start with a concept, and maybe we would go and we would, on the point right here, but we were maybe starting with a 3D printed plastic deflector, and that would really let us kind of look at the application from a macro point of view about where that water's going, and refine it and make a very quick decision on saying, hey, this is something we want to pursue more, or no, this is something that's not going to work. So, and from that, we would go from a 3D printed, say, deflector to 3D metal printed deflector, just kind of refine it in, getting closer to what our final product would be, until we finally get to our finalized production stamping. So being able to utilize some additive manufacturing processes to prototype these guys was really very helpful.
Let's move fast.
It lets us move fast, and it lets us really shorten that design iteration time where, in the past, you would have to go make a tool, wait for those prototypes to be made, flow it, and then as soon as you flow it, you're like, okay, I got to make a change. So that means a tool change. In this case, we can go print another deflector. We can make real quick decisions on what we want to do. So we spent a lot of time in that design iteration cycle, and again, collaboration back and forth the whole time. Hey, this is what I'm seeing, guys. What do you think? And one thing to note about the design cycle itself, in this case, it was very fluid. As we were learning new information, we were trying to digest that and make decisions, as we got that information. Most typical of another project is we've got a pretty good idea of what we need to do, and we can lay that out into a proper scope, and it's more of a kind of a linear flow from a development standpoint of, hey, this is our goalpost, this is where we want to be. But in this case, hey, we were learning as we went along.
There was a lot of information coming in throughout the entire process. That would either change your thinking or force you to make an adjustment to what you were trying to accomplish.
Matt or I could get several phone calls in a day from Phil, bouncing ideas of stuff that he's learned, or niches that might be in the configurations that we need to take into consideration. But that level of communication was key, and not only on the design side of it, but getting a product made, getting it prototyped, getting it tested. That's only half the battle. We still have to make it at scale. We have to make a product that continues to have the quality that's expected of our products, and so just as much needs to be said about the fact that our entire organization was on board that this is a priority. Right? So even if we had a product that was satisfactory from a testing standpoint, we had to make sure that our procurement team had the supply chains in place, that our manufacturing group had all the tooling and any fixtures and whatnot ready to go, that they could run at rate, they can run at scale. And our quality department has got all the I's dotted and the T's crossed, and that ultimately we can make a product that not only works in application, but can be manufactured repeatedly at scale. So I think one thing to really highlight on this, at least for me, that stands out is the speed of the total project. I mean, we're coming in from initial discussions to product on the market in right about a year's time. A typical sprinkler project could take 2 to 3 years.
Yeah.
just based off of, just trying to get that whole entire design cycle in mind. But we had some good partners, some good collaboration, both internally and externally, that really facilitated a very quick design and time to market cycle.
Maybe you mentioned or talked a little bit about some of the things that we're able to do here that let us get through the regulatory or the UL or FN testing requirements quicker.
Yeah, so we talk a lot about the performance of a product on fire, and we're going to see some of the fire testing here in a little bit, but what's as important that we have to do for every sprinkler is all the mechanical testing behind it, right? And we're able to leverage our lab that we've got here to be able to go out and make sure that we're going to be passing and that we're up to snuff for all the other mechanical testing that occurs just like any other sprinkler. So we're looking at making sure there's no material compatibility issues, making sure that strength is up to par for all the components that go in it. We're looking at corrosion issues, all those things that we can do because we have those tools here in house. When we go to our agencies, that we can have a lot of confidence that we're going to be successful because we can mirror those tests here.
Yep.
And make changes before we get there. And we know that it's going to be a robust product before we even get to our labs.
Yes, I mean, to be able to know that you're going to be able to get through a 90-day mechanical test, for example, like that, at an agency is critical in terms of being able to move quickly.
And it's not always trivial. So you want to make sure there's a lot of work that's put into all these, if you want to call it behind the scenes tests.
Sure.
But that's part of making sure that every sprinkler that is listed is of the best quality.
So we've talked about the speed and then also the collaborative effort and all the things that we were learning. And I think that makes me think about as we started to dig into this and we sort of already were going down this path, we also started to realize that this is an opportunity and a need that exists. And it's something that is really, I think everybody recognized that it was something that was needed now. We started looking at the projected battery manufacturing over the next 7-8 years. And I have a slide here that covers that and kind of talks about what that looks like. And so you can see here, if we have the slides up, this is the projected demand for lithium-ion batteries over the next up through 2020. And of course, the growth is clear that there's going to be a lot of growth. What's really interesting is to look at where that growth is going to occur. And a lot of it is in electric vehicles. And interestingly enough, that's sort of how we got started down this road, is looking at battery manufacturing facilities that were going to be supporting the electric vehicle demand over the next 10 or more years. We have a map as well that sort of shows where that's occurring. You'll hear people talk about the battery belt. And so these facilities are being built now as we speak. We're constantly having conversations with contractors and customers and consultants and end users about these facilities, and specifically these areas in the plant that we talked about, touched on a little bit.
I guess there's also going to be a lot of questions there. This is new for the HJs, right? They're wanting to, they have a vested interest in understanding what's coming with these facilities that are coming into their jurisdictions.
It really is a huge issue for the HJs. I think one of the things we should talk about is what criteria is out there now or was out there, where it came from, and that sort of helps color in why we felt it was important to do what we did. If you look at these formation and aging areas in a battery facility, so this is what the process looks like after they've made the cells. There's different types of cells. We're going to talk about that a little later. But the battery manufacturing process is like many industrial manufacturing processes. It's a multi-step process, but the first thing you have to do is they have to actually make the cells. And then once they make the cells, they go into these areas that really look like a large warehouse or storage room, and they call them aging rooms. I mean, you have standard temperature and high temperature aging rooms. But those rooms have, like I said before, those are the really large rooms that have floor to rack, floor to ceiling racking. And the in-rack sprinkler installation really was clearly a challenge. Well, I think it's worth talking about what they were trying to do and what the basis for what they've been trying to do is. And it all goes back to some work that was done in the mid 2010. So around 2013 to 2016, the National Fire Protection Research Foundation sponsored a project, and they went in, and it started with just looking at and characterizing the hazard of lithium-ion battery cells. And then eventually they got to a point where they said, well, we should run a test. And so they did, and the test they ran was of pouch cells in cardboard cartons in a double row rack configuration. Very different from what you see in a manufacturing setting, but maybe more common of what you would see in a general storage warehouse. And the test that they did, is worth talking a little bit about it, because I think this is the background or the basis for some of the criteria that's out there today. The test they did was, again, they were with 20 amp hour lithium-ion polymer pouch cell batteries, and they were in double row racks up to 15 feet tall under a 40-foot ceiling, and they used a K22 at 35 psi. So they did an under one test, and an under one test, as you know, as you both know, that's your ignition location is under one sprinkler. And they had one sprinkler operate, and it was a very successful result. And so the work that they did, they also did some medium scale testing, and then they published some reports that are available online, and it had some guidance in it that essentially led you to that helped people figure out how to protect lithium-ion batteries in a general storage configuration. In the middle of our project, FM published some criterion 8-1 that was based on that. And that criterion, you can see it here. It basically says that if you've got a 40-foot ceiling and you only have 15 feet of storage, which is what the test was, that single test they ran, then this is what you do. I think they do they tell you to use a K25 or a K22 sprinkler. But if you have a building that's taller than that, or you have storage that's taller than that, they're essentially using Scheme A from 729. And so that's what's out there now. And it's really was a challenge for these sprinkler installers when they're told by a consultant or whoever to go, hey, go protect this battery formation room using Scheme A. And it's sort of a round peg through a square hole kind of problem. And so that's going back to what led us to, there's got to be a better way. Let's look and see if we can develop something that's easier to install and is based on large scale testing for that specific application.
So that probably leads us into a good time to talk about, that's where we're at. We've talked a little bit about the development cycle. We started going down this path of thinking about sidewall protection in rack, which in of itself is a novel concept, but really in the scope of talking about these lithium-ion batteries, probably a good time to talk about our next steps after that, which was how are we going to get, who are we going to work with to bring this, a listed product to the market? How are we going to do that? Because there's not existing standards out there from an agency standpoint of listing for this type of commodity or there's not a lot of guidance out there. We were kind of writing the book with this.
Yeah, the book certainly needed to be written. That's true. We decided to go to UL, I think, because UL's been doing a lot of work on lithium-ion batteries because of their 9540A standard. They've got a team of folks that are really focused on the lithium-ion battery fire hazards. And there were a couple of things that we had to deal with. And one was there's not a listing standard for us for a storage horizontal sidewall sprinkler as an in-rack sprinkler. And the second challenge was there's not a lithium-ion battery standard commodity to test against. And so you really need those two things if you're gonna move down the path and get a listing, which is important. And so that we sat down with UL, we had a conversation with them, and they were willing to. They saw the need as well, and so they saw what we wanted to do, and were willing to work on a standard that both us and others could use that they wanted to try to do.
So it almost venture to say they're enthusiastic about the project.
Matt, they were enthusiastic about it. I don't think at the time they had really done any large scale sprinkler testing at their facility. A lot of it in their other labs, they had done work. We certainly had gone and seen, I shouldn't say no, they've done battery energy storage stuff in the large scale building and mock-ups of that nature. So
we got to bring in and meet a whole different group that's just working on battery research there that come into the fold and really helped us drive the urgency of this. That's a whole group of people that we typically have not worked with in the past, but
that's right,
an integral part of this process.
Right. They've added folks to the team that were really focused on batteries, and wonderful folks to work with. So you maybe talk about a little bit about what we did in order to get into our large scale testing. Matt, what are some of the things that we had to do in order to get the racking built? Maybe it's helpful to show what that racking looks like.
Because this isn't something you can just go get. Right?
Yeah.
We were making, we were helping. We had to make these racks, and you were the driver behind that.
Yeah, fortunately, I had that excellent opportunity to be involved with that process. So, going from wood constructed, collection racks, to go ahead and get a steel fabricator on board to design and build the racks that we could get shipped out there. That was a real interesting challenge, because typically that's not something in my daily duties I'm involved with, is designing racks and having them fabricated. Now on the piping installation side, that's more of my expertise. So once we had the racks built and shipped to UL, I had the opportunity to go out and install the fire protection piping for those scenarios.
You had them build some racking that was very robust and able to withstand, I think now, more than 7 or 8 different fire tests. So those will always be appreciated. We have some images of what they look like, and then we talked a little bit about not having a commodity to test. So what did we decide to do?
So that was all part of the process of thinking about how do we get from no standard to something that has value in the market. So we went to exposed expanded commodity there, and that's what you see. You got up in the photo there, and that's what our initial testing was done to get our Group A listing on that, correct?
That's right. So we
which, if anybody knows anything about the testing, right, that's a tough commodity to work with. That's extremely aggressive.
But many would agree that exposed expanded or uncartoned expanded Group A plastic, which is polystyrene meat trays wrapped in plastic, is the most challenging plastic commodity to protect. Maybe might be some debate on that, but they're very, very challenging fires. And so this image shows one of the test setups for our listing series. And the listing test series went really, really well. I think, as we continue to march through the tests that we each day, and we were really starting to really get excited about, man, this really does, this is really effective and it really does work. And so
UL was doing what they should be doing, right? They were throwing
hard on
difficult
us.
scenarios at us. And,
They were.
you know, they were making decisions as we
Yeah.
were testing on, you know, what the next scenario would be as far as ignition
Yeah.
locations and whatnot. But
That can always feel a little frustrating at the time, right?
Yeah.
Thinking, well, I thought we were just going to have to do this many, but then they certainly did their job and their diligence, and we got through that test series really well, and ended up with a listing that is all outlined and documented in our bulletin. We've got a little bit of that information up on the screen for those of interest, but basically the sprinkler is listed to protect all of your standard commodities, class 1 through 4, and all of your group A plastics. So it really does have broad application outside of the battery world. It is listed to a very specific racking configuration, and the listing calls for 4 sprinklers, 2 on 2 lines, and each flowing at 60 gallons a minute each. That's not a lot of flow when it comes to an in-rack protection scheme. So one of the things what did we want to do next?
yeah, so, you know, this was all well and good, and it's great. It was great progress to get that on a standard commodity. But our ultimate goal is to get some test data on batteries.
On actual batteries, yeah. And so before we dive into that, I think it's worth spending a little bit of time and talking about lithium-ion batteries and some of the terminology that you hear people use when they talk about lithium-ion batteries. And so you'll hear people talk about 3 different types of lithium-ion batteries in terms of configuration. So there are prismatic cells, there are cylindrical cells, and there are pouch cells. And so there's an image of all 3 shown here. But all of those different variants can have the same chemistries, and the cells we elected to test with were the cylindrical cells. And so we tested with 18650 cylindrical cells. We've got one here. There's a couple on the table in front of me as well. And I'll talk a little bit about what that terminology means. So when someone says it's an 18650, those numbers mean something. So it's 18 inches in diameter, 18 inches across. Millimeters. That's hardly 18 inches. Thank you. It's 18 millimeters in diameter and 65 millimeters in length. And so there are different sizes of cylindrical cells, just as there are different sizes of other cell types. And so I think Tesla's right now working on a 4680 that you'll see in the Cybertruck and maybe in some of the other models of vehicles. That's like the size of a Red Bull can, bigger. And it's sort of the same situation with prismatic cells and your pouch cells. They come in different form factors, come in different sizes, and they have nomenclature related to the sizing as well. And so I think an important distinction too to make about your prismatic and your cylindrical cells is those are typically in a hard case, whereas your prismatic cell is in a soft pouch material. So always interesting to look and see what's inside the batteries. And so this is an X-ray. You can see an X-ray of the jelly roll inside a cylindrical cell. And you can see the layers. And so there's different layers within the battery, and there's a separator between those layers. And so here you can see what the jelly roll looks like from an end view. And if you look at it unrolled, and then maybe some diagrams to bring a little bit of clarity to it. So the batteries consist of a cathode and an anode and a separator. And then on the cathode is typically a graphite material or something, and that's where your cathode chemistry would exist. And so you hear people talk about cathode chemistry or cell chemistry, and some of your cell chemistries that you'll commonly hear are like lithium iron phosphate is one. nickel, cobalt, aluminum is another, nickel, cobalt, manganese. And so the cells that we tested with, we'll talk a little bit about where those fit within all of those different descriptors. So there's one other thing that we want to touch on, and that's state of charge. So to go back, the testing that F and Global did was at 50% state of charge on those batteries in that large scale test. And state of charge does have an influence on heat release rate and intensity. And so we've been talking for a while. Let's watch a fire test. And so this test that we're going to see is 160 of these 18650 cells at 100% state of charge. And this test was done at UL, and this is before we got into our large scale testing, while they were separately trying to characterize which battery should we use in a large scale test? What's the right thing to?
No protection on this particular.
Thank you, Matt. This is an unsprinklered test, so you're just going to get to see how these burn. So I'll go ahead and hit play here. So as you can see, as we saw, they're very energetic fires. And essentially what you saw there is what they will talk about and what we'll see again as one cell goes to the thermal runaway, and very quickly you have what's called cell to cell thermal runaway propagation. And that process without intervention happens very quickly, and it's very energetic. And you can imagine translate that inside of a building, that could be very impactful in a negative way, right? So, as we were talking about, what we wanted to do was a test with actual lithium-ion batteries in this racking arrangement with our new protection scheme. And so we got about 8,000 18650 cells. And there was a lot of, I'm not sure if we want to do this from our partners, but they were willing to run the test in the racking configuration with our protection scheme. And so
At 100%.
at 100% state of charge, which we figure if we're going to do this testing, we might as well try to bookend it, right? We might as well make it so that people are going to need to use it. They don't have to, we test at 75% state of charge and they go, oh, but our batteries are at 80 or however that might look.
Audio is shared the computer. So if you want to unshare and share for the next test.
Roger that. I was just notified that you didn't get to hear the sound. So we're going to see if we can fix that for the next.
Yeah, that
for the
audio
next,
would
the
help
audio,
reinforce the apprehension.
the audio is of the test is good, and we'll see if we can make sure that works for our large scale test. So again, they were 18650 cylindrical cells. The chemistry is nickel, cobalt, aluminum, which is one of your more energetic chemistries, 3,500 milliamp hours, and the 100% state of charge, as we talked about, and we put them in plastic formation trays. And so what's interesting, if you look at these formation trays, you can see there are holes in the bottom. And those holes are so that in the manufacturing process, they can get to the charging terminals on the bottom and the top while the trays sit. and about 8,000 cells in the test configuration. So there's about 3,800 cells on the bottom level.
You draw a parallel, that quantity of cells to like a Tesla.
A Tesla Model S. Yeah, also that's a good point, is that number of cells is about what you'd see in a Tesla Model S. And I think they still make the Model S with that battery. Diagram of the test configuration. This is a plan view. Interesting, and you'll see this when you see the test video as well, or you might be able to see it, is that the target arrays, we had no sprinklers in the target arrays, and we had carton unexpanded commodity in the target arrays. Similar to what FM Global did in their testing, and it's a more cost-effective strategy. This is the test in elevation view, the test layout. You can see the vertical and horizontal barriers, and the dark purple trays are the ones filled with batteries, and then the surrounding lighter colored ones were filled with sparsely populated batteries that had that UL's team put thermocouples on to look and see if the fire would have spread outside of that main array. So let's see if we have sound here. We can still watch it, and if we don't have sound, we will have sound on the recorded version. That's the video.
Regardless, you're gonna see a visual.
Yes, the visual fire.
Well,
Here our cells have gone into cell-to-cell thermal runaway, and the first sprinkler quickly operates at 206.
this was my first time seeing a battery test in person, but really, here, you know, we got these one video one. You know,
Yeah, that's correct. I mean, been to UL lab many a time, but definitely the first experience was my bad.
it was, the video that we're showing is set up slightly, but it is, in person, it was the amount of energy that's released when the battery starts going into one of us, it's hard to describe. It's the video being sped up, you kind of have an anticipation when you were there in real life that, you know, is anything going to happen? Is anything going to happen? And then it's just like a light switch gets thrown when the first cell goes into runaway, and the release of that energy. It's pretty impactful. It was pretty impactful visual being there, even watching it out of the control room.
Yeah, and the video is only sped up during the time between when the igniter was ignited and up to just before the start of thermal runaway. And so the rest of it is in real time. And as you can see, it's quite dramatic. There were people before the test that said, there's no way you're going to stop cell-to-cell thermal runaway propagation. Can't do it. And so we were very pleased that in the end it did. And I made a incorrect statement a minute ago. The first sprinkler operated at 2:11, 2 minutes and 11 seconds. Thermal runaway started at 2 minutes and 6 seconds. So here you can see the damage and some of the aftermath. And I think only about a third of the cells in the main array were consumed. And so it did a really good job of stopping cell-to-cell thermal runaway propagation. And it really highlights that a key to solving or addressing these problems is really a heat transfer issue. You have to cool the adjacent cells if you want to prevent them from being a victim of as an adjacent cell going into thermal runaway. And so if you want to put that process, if you want to put a stop to that process, you really have to have a strong impact on the heat transfer process that's going on.
Even looking at the photo you got up right now, just thinking about the mass, just the mass in general of the batteries in that cell, you can see the ones there, not damaged, right?
Yeah.
There's, you know, it's done a great job of containing that, and the upper rack wasn't even touched, right?
Yeah, I like to tell the story about the battery engineer who was there from a battery manufacturer and said, "You're not going to throw those away, are you?" And so, of course, that led to a discussion, but that they did get thrown away, and they had to be recycled. Excuse me. And so we have put a bunch of information online on our website for people to access. We think we've got something that is really solves some problems for the industry. There is a lot more work to be done in the lithium-ion battery space, but in terms of a protection solution for batteries in manufacturing, this is a solution that is fully tested. It's one of the only actually tested solutions that I think exists on the market. And so it's going to be exciting the next 10 years, I think, and to see the continuous developments. We continue to run large scale testing and look at what might we consider doing next.
Yeah, so say, we're actively still working.
Oh,
Right?
sure.
This is
Yeah.
not the end. We are in process of looking at other schemes and as we speak, right?
Yes, as we speak.
Yeah, looking at those construction projections, it's not gonna slow down, so we have to be at the forefront.
Plenty of work to do. Well, that's all we have for today. Let's open it up for any questions that might come from the audience.
Yeah, thank you guys for the presentation. There are a bunch of questions from the audience in the chat. So let me start out maybe early on in the presentation at the battery cell level. And there's a question about, do you know what causes thermal runaway, and can it occur in batteries when they're only charged to, let's say, 40%?
Yes, so that's a great question. Yes, thermal runaway can happen in a battery that's only at 40% state of charge or less. And maybe the answer to the first question last is thermal runaway is caused by a number of different things. It can be imperfections in the manufacturing process, mechanical damage to the cell, abuse of the cells in terms of if they're exposed to temperatures, overcharging. A number of different things can cause thermal runaway in a battery. And I'll tell a quick story. You see in all these e-bike e-mobility fires happening, and we know of people that have had fires that have either their power tools or things like that while they're charging. Where I live, there's a bike store, and they were delivered a crate of new e-scooters to try to rent out to the people that wanted to rent them out. And I test drove one of them. Now, these didn't have a UL listing, but they took it for a test drive and drove it back in. And while not even charging that night, a fire occurred and it burned the store down.
So we've got some questions about the benchtop test that you showed. One of them is whether there were any measurements of heat release rate taken of that test or some similar test.
Yes, there is heat release rate data for that test. I think if there was someone that was interested in having that information, we could probably get it for them. that was one of a number of different tests that they did with different batteries and things like that. And there's also a lot of data out there on bench scale testing of batteries at different states of charge. I think there's a report that was done for the FAA that has a lot of heat release rate data in it related to batteries at different states of charge.
Yep. And there's a couple of questions that came in, and these were actually back when you were showing that benchtop test in the presentation, but I think it also applies to the full scale test. A couple of questions about conditions at the ceiling during the test. So whether the ceiling height would affect the test results, and if you have any concerns about structural damage to the ceiling structure prior to control by the sprinklers.
Yeah, it's a great question. So I don't remember the exact ceiling height that we had set at UL. The design and the system is intended to operate without causing the ceiling sprinklers to activate. So if you can stop a fire like this in a couple of minutes and really immediately have an impact on the heat release rate, I don't think you have to be too concerned about structural damage. So hopefully that answers that question.
Just from a visual standpoint of being there in person, you never saw that fire rise above the racking system. I mean, it was knocked down pretty well.
The initial fireball certainly got above the racks, right? If I remember right. But that was a very, very short-lived event.
And is there any concern, and how do you deal with rocketing cells?
The cells rocket, and that is I think that's a feature of cylindrical cells and perhaps prismatic cells as well. So we have not yet focused on what should be done about that. I do know this in the test that we showed here, those cells didn't rocket and cause adjacent materials to ignite. And I think the rocketing really drives home the need to make sure that all the surrounding things have adequate protection as well.
Yep. And then there's another question. There's a question about whether the sprinkler is intended to be tested for FM approval, or is it only designed to comply with the UL specific application listing?
Yeah, well, it's only been tested to the UL specific application listing, and I'm sure we'll be looking at engaging with FM Global about going down that path. And they're in the same situation I think that UL was, where there's not a standard there to list against. They've published some criteria. I think that we'll see some of that criteria evolve as as more information becomes available, as more testing is done. Hopefully that answers that question as well.
Yeah. And then see what else is here. Ooh. Any research going on that we're doing using like an encapsulator agent in F500?
We are not currently looking at an additive for the water. Now, that doesn't mean we might not consider that in the future, but I can say from all of the testing that we've done is that in this application, water does a really good job by itself. And we may look at doing something like that in the future, but right now we're currently not pursuing that.
So the questions keep coming in. I'm going to keep going for a little while longer here because we have some more time, and want to make sure we answer everything we can. So is there a guard available for the sprinkler at this point?
We did not manufacture or design a guard for the LB11. And the reason we didn't do that is because most of these systems are automatic storage and retrieval systems. They're robotic, and there's we weren't seeing guards on the systems or on the sprinklers, uprights and pendants that were installed in the facilities that we've seen. Doesn't mean that we might not do that in the future. It is a sidewall as well, and so it takes up a lot less space, and it's, I don't think it's as at risk of being hit as maybe an upright or pendant might be. But that's something we can look at.
And we've got, you know, fusible link.
And it's a fusible, that's a great point as well. And it's a very, the fusible element sprinklers, for those who don't know, are very robust. So.
And there's some questions about NFPA or FM guidance on requirements for lithium-ion battery storage rooms. Can you just give a brief overview of what's out there and not out there in terms of NFPA requirements and FM guidance?
Sure. I think if you're in general storage in a warehouse, you may want to look at FM data sheet 8-1. There's some criteria there. I think you want to look at that with the understanding that what it was based on, and we covered some of that here. And so there's that guidance that's out there. And then NFPA, as currently the Standards Council has tasked the 855 and NFPA 855 committee with addressing storage in their standard. And so I was at the more recent meeting of the 855 committee last 2 weeks ago, and they're working on that. And we're trying to participate in that process as well. But there's not a lot out there. If you look at NFPA 13, it excludes lithium-ion batteries from the standard. And so we'll see where it goes. You may see it bounced back to the 13 committee. I certainly feel like that's also an appropriate place for criteria, but there's not a lot out there now. And so I think many folks find themselves trying to look at a performance-based approach. And of course, one of the best ways to do a performance-based design is to do one that's based on large-scale testing.
So there's also several questions about either barriers or wire mesh within the racks.
Yes.
What have you seen out there in the field as far as that's concerned?
Right. So the wire mesh in the racks, I meant to cover this when we were talking, that was there to make sure that as we have a live flame underneath plastic battery trays, that the trays stayed in position, because what we were really trying to focus on is we didn't want to know how the sprinkler performed against a plastics fire. We already knew that. And we wanted to see, how does it perform against an actual lithium-ion battery fire? We go back to the testing that FM did, and in that large-scale test, the batteries actually didn't get involved. And so one could say that testing shows you if you can protect the packaging, then you can protect batteries that are within that packaging in a storage configuration. So the wire mesh was there for the test, and we had it there. We've run additional testing, and we got rid of the wire mesh, except for on the underside where we wanted to make sure that the battery stayed in place while we were trying to get them going. How about that?
So there's a question about whether water can fully put out a lithium-ion battery fire or just suppress it until the fire department arrives. What have you seen in the test?
Yeah, that's a great question as well. And so in that test, we showed you the beginning of it, right? And so the first 3 minutes, well, that test ran for a lot longer period of time, 30 minutes to be exact. So after the first sprinkler operated, the water ran for an additional 30 minutes, which is a standard test duration at UL. You do any large scale listing test, 30 minutes is the recommended time. And then they let it sit for an hour to see if any of the cells reignited. And so I think the question was, can water do it alone, and I think that answers that, yes, there's a potential for that. You do hear a lot about fire departments having challenges with electric vehicles. And I think one thing to keep in mind is once these batteries come out of manufacturing, they go into packs that are enclosed. And those enclosed packs, it's difficult to get water into them, or any agent for that matter. And so, the fire departments come and they struggle with those events. But I think in this application, water appears to be a very good solution all by itself.
And it looks like we have a couple final questions here. One of them is just clarifying the hydraulic design in the UL listing for the sprinkler. Is it required to be balanced with the overhead system?
It is not. And so I probably glazed over that when we were looking at the data sheet information. But so you don't have to balance with the overhead. And so typically, if you were going to use the LB11 specific application approach, your in-rack demand is going to be quite a bit less than your ceiling demand would be. I think we're talking about 240 gallons a minute total with 4 sprinklers operating, and most ceiling systems would be 1,000 or more, depending on what you have there.
Yep. And maybe there's a couple more questions here. Then one is about any concerns with water reactivity with the lithium.
Yeah, that is a great question that comes up. And so, and there's videos that are floating around in our online world that show, maybe someone taking a battery apart, pulling the lithium foil out of it and tossing it in water and watching the reaction. So most lithium-ion batteries in use today, the rechargeable type, do not have lithium metal. And it is a distinction. Lithium ions are different than lithium metal, and it's sort of like solid sodium. If you could get a thing of solid sodium and throw it in water, it would explode. But we drink and eat sodium chloride, so we drink table salt all the time. So it's kind of that difference. And I've heard some people talk about they're looking at developing rechargeable lithium metal batteries. And again, it's the lithium metal that's water reactive. And the thinking there is that those will be in a hard enclosure. And so again, it's going to be more important to deal with the heat transfer process and prevent it from spreading to adjacent cells. But the industry continues to evolve, and we'll see what happens down the road.
Do you have any guidance for the situations where you might have a different clearance between the sprinkler and the commodity, different height of commodity, how you would apply the sprinkler in different configurations that might exist out there?
Yeah, I think are wide open to working with people that have different configurations. It's what I spend a lot of my time doing, is engaging with engineers and end users who want to talk about different storage configurations, clearances, and all of those kinds of variations that you're bound to come up with if you're actually having to design and install something. So I think we would be that, that's probably a more detailed conversation to have offline. And please reach out. We'd like to get into the weeds and figure out real problems with people. Okay.
Well, thank you very much for that. I'm gonna there are a few more questions in the chat that we'll go ahead and answer there. And it looks like we've reached a little bit past our time limit. So we'll go ahead and wrap it up.